Okay, good afternoon. We'll start today a new topic. In last lecture, we finished uh, Faraday's laws and Lenz's laws, along with the Ampere's law. Today, we will look at the inductance. Okay, so we said that we have looked into the electromotive force induced in a coil when this coil is experiencing time varying flux crossing into that coil. So what is this inductance? As you can see, this uh, technique is already utilized now in wireless charging, where you have the charger generating time varying magnetic field, and the mobile phone is receiving this time varying magnetic field through coils also that are in that mobile. The time varying flux is resulting into an induced electromotive force that is used to charge the battery of those mobiles. So this is one of the applications that Faraday's law has been utilized in, and this is in the recent few years. Uh, Now let's move on to where did this inductance come from? If uh, if you recall the magnetic field induced by uh, a solenoid, or let me call this one like a coil that has a cross-section area of A, is given as B magnitude equals to mu naught I n, where n is the number of turns per unit length. So if I look at the flux, then the flux would be the magnetic field times the area vector. If I have them in parallel, then theta is 0 and the flux would be BA, right? Then d phi over dt is d over dt BA, and this is going to be b phi over dt equals to uh, d over dt mu naught in A. So if I take the mu naught n A outside, I end up with mu naught n A di over t over dt. But what is a mu naught n A? Mu naught n A, if we recall here, we have phi equals to mu naught n IA, which means mu naught n A equals to phi over I. So if we substitute here with phi over I, then d phi over dt would be phi over I di over dt. And we define the phi divided by I as the self-inductance of this coil. So d phi over dt equals to L di over dt. And if you recall, this is the electromotive force. So the voltage generated across a coil that is seeing a time varying current is basically time varying current that is induced is going to generate an electromotive force between the terminals of this inductor. So this is the relationship of the induced electromotive force with respect to the time varying current and inductance. Okay, so having said that, then we can say that that this inductance basically that is given by the phi divided by I will have the unit of Henry. So 1 Henry is basically 1 Tesla meter squared per ampere. And this is the circuit symbol for the inductor. I is the current that is going through the inductor. As we will see, we can look at the inductor as two different models. It's an inductor that has been used that is coupled through the time varying flux to generate a current, and an inductor that does exist in a circuit where it's been treated as a passive component more than receiving and re-inducing the current. Okay, so the inductance by itself measure how much opposition a loop or a coil offers to a change in the current in the loop. So if I am to look at this inductor as a component that is seeing a time varying flux from external magnetic field, then the induced electromotive force across it would be delta VL, or sometimes VL equals to minus L di over dt, while the current is entering the positive terminal. So again, those inductors, they oppose changes in the current with induced electromotive force. So to understand what does this mean, if I have a time varying flux or magnetic field going from the left to the right, increasing, then basically this is going to result into an opposing magnetic field. And in this case, delta VL would be plus at the increasing, minus uh, at the other side, and the delta VL would be minus L di over dt. If the current is, or the magnetic field is going in the opposite direction, then an opposing magnetic field will go into the other direction, trying to compensate for the change, and this is going to result into induced electromotive force such that the positive is where the magnetic field is pointing or decreasing here. The current is going in this direction, decreasing, meaning that the magnetic field is increasing in the opposite direction. So you always have an opposing magnetic field trying to compensate for the change in the external magnetic field, and this is going to result into a current in the direction such that the right hand rule is maintained. Okay, so let's look now at the inductor in a circuit. So when we studied the capacitor before, we have seen how is the capacitor that being charged and discharged behaving. Was exponentially charging and discharging. The same thing is happening here, however, for the inductor. The same thing is happening to the current of the inductor. We will see that when the current start to build up into the inductor, the response also is going to be exponential. So if I am to look at the circuit, and to see how is the current is building up in the circuit. Then when the current is building up, it will build up also as exponential, which means was zero, and then right at the switch, when the switch happened, we will see that the current will start to exponentially increase till it reaches the maximum. And this maximum would be whatever maximum current will be in the inductor right at the infinity. So let's assume that this is I naught. So the same thing is happening here for the inductor, but however this time is for the current. So we will see that after 1 tau, we would be already achieving the 0.63 of I naught. We will be achieving 0.63 of I naught after a tau. After 5 tau, or you can use t equals to infinity, you'll be reaching the steady state. At that point, the maximum current would be I naught, which is the maximum current that a voltage source can give to the inductor, because at the infinity, as we will see later on, the inductor is treated as a piece of wire, nothing but a wire. Now, the same thing is going to happen for the inductor when the current is being uh, this, when the inductor decreases in its energy or start to dissipate its energy, the current will start to also decrease exponentially. Where if the current was at this level, then you will see that the current will start to decrease exponentially till it goes down to the zero if the inductor has no other sources. Then again, after one tau, this this value would be 0.36 of I naught after 1 tau, and then you can say after 5 tau, or after t equals to infinity, the value of the current will become zero if the inductor has no other sources in the circuit to start to give a final current for. Same thing, the same thing, of course. It will settle down to whatever current is available for it in the circuit. It will settle down at the t equal to infinity. It will be treated as a piece of wire, and whatever sources you have in the circuit that determines this current to be, it will follow uh, that value. So I'm gonna come to this in the coming example, how we treat the inductor at several conditions. So, but what we need to know that the inductor is also changing, the value of the current in the inductor is also changing exponentially. Either either the current is building up in the inductor, or the current or the energy is being in storing more energy, or the energy is being dissipated in the circuit. In both cases, the behavior is going to be exponential. Okay, I is the current. Okay, so exactly. The however, in the capacitor, in the capacitor, we were treating the voltage as the continuous uh, value in the capacitor. However, in the inductor, we will be treating the current as continuous, while the voltage can change abruptly. In the capacitor, the voltage is continuous and the current can change abruptly. Yes, tau in this case for the inductor, it will be L divided by R. If you recall, tau for the capacitor, this is for the inductor, tau for the capacitor was RC, tau for the inductor is L divided by R. And always be careful when it comes to this. Here, this is the maximum current. The maximum current in my circuit here at the infinity, where basically the inductor would be a piece of wire, is epsilon divided by R. Other circuits may have different I naught, but this is the I naught here, means this is the maximum current that my inductor is going to achieve right at the t equals to infinity. And this is also the maximum current or the current that I'm starting from and then decreasing exponentially. Again, this epsilon over R really belongs to this circuit. Those values, they may be different variables in other circuits, but this simple one loop circuit, as you can see, the maximum current would be epsilon divided by R. Okay, so let's look at this question and see how we can treat the inductor when it comes to uh, calculating the voltages or the currents. Consider the circuit with S1 open and S2 at position A. Switch S1 is now thrown closed. At the instant it is closed, across which circuit element is the voltage equal to the electromotive force of the battery? Okay, so what we understood is the circuit was switch S2 was put at A, and then I have this battery here, and then I have switch S1. This is switch S1 was closed at t equals to 0. Okay, so I need to find across which circuit element is the voltage equal to the electromotive force of the battery. So now once you hear at the instant it's closed or right after it's closed, I mean the moment of t equals to 0 plus. This is the moment right after the switch is closed. So if the switch is closed at t equals 0, so I need the moment right at t equals 0 plus. So now let me close this and let's evaluate how how much the voltage would be. The current in the inductor right at t equals to 0 minus, which is before the switch was closed, was 0 because it was an open circuit. So it was 0. The current into the inductor right before the switch was closed is 0. Now, remember what did I say about the inductor? I said that the current in the inductor is continuous, which means it does not jump, does not have any abrupt jumping in the values. It has to be continuous, which means that the value of the current across the inductor at 0 minus should equal to the value of the inductor at 0 plus. What does this mean? This means that indeed the inductor right at t equals to 0 plus, the inductor current would be 0. So the inductor current should be 0. What does an inductor, what does a 0 current in a component mean? This means there is no current going into this component, which means I can remove this inductor and it will be replaced by an open circuit. So if I replace this inductor by an open circuit, because its current is 0, then this means that the potential here will show up here, and the potential here will show up here, and the potential here at the negative electrode of the battery will show up here. So if I put this one A and B, then this potential here will show up at A, and this potential here will show at B, and indeed the VL will be equals to the epsilon, which is the voltage of the battery. So right at the instant the switch is closed, the voltage of the battery will show up across the inductor, because the value of the current right at the t equals to 0 minus equals to the value of the current for the inductor at t equals to 0 plus, and both are zeros. Then you can replace the inductor by an open circuit, and the voltage is going to show up across the inductor right away. Is this clear? So the answer to this problem would be B, the inductor. Questions? It will start from from the maximum, and then it will decrease. Yes. When the switch was open, definitely the current was 0, because there were no energy stored in the inductor. So the current was 0. Right after I closed the switch, the current at that moment was still 0, and then changes exponentially. Okay. So the answer is B to this question. Now let's move to the next question. In this question, we have an inductor connected in parallel with a 2 ohm resistor. Both are connected in series with 1 ohm with 6 voltage with a switch S. Now the question is asking to consider that switch S is closed at t equals 0. What is the voltage across inductor L just after the switch is closed? So we are talking here, we're talking about 0 plus. You got that right. So we're talking here about about the 0 plus. So if I am to redraw the circuit again, if I am to redraw the circuit, I have an inductor here. Then I have a 2 ohm resistor with 1 ohm, and a voltage source. Now, the switch is closed at t equals 0. So I have the switch closing at t equals 0. What is the voltage across the inductor L just after the switch is closed? So I'm interested to calculate the voltage. I'm interested to calculate the voltage. So when the switch was open, the current was IL at t equals to 0 minus. I have IL equals to 0. Now, when the switch closes at t equals 0, I have t as 0 plus, has to be the same. So IL will also be 0. If IL, so now this is 0 plus. This is the moment of 0 plus. So IL 0 plus here is 0. IL 0 plus is 0. 0. There is no current going into this inductor, which means the voltage across the inductor would be the same as the voltage across the 2 ohm resistor. So I have now this current generated by the 6 volt only going this way through the 1 ohm and 2 ohm and coming back. This is only at 0 plus. This is only at 0 plus. Eventually, the current will start to go into the inductor, and the current will start to exponentially increase. But right at t equals 0, here, this is 0 minus, this is 0 plus. Right at this point, the value of the current is 0. So if I want to calculate the voltage across the inductor right after the switch is closed, I mean the 0 plus, the current is 0, then the voltage of the inductor will be equal to the voltage across the 2 ohms. So I need to first find I equals to 6 divided by 1 plus 2, and this is equals to 2 ampere. Then the VL equals to V2 ohm equals to 2 times 2, and this is VL is 4 volts. No, the current is 0. The current is 0. The voltage is the same voltage as the 2 ohm resistor. This is again only at 0 plus, only at the moment right after the switch is closed. Okay, any question? Any question? Is this clear? Okay, that's good. That's good. So let's move on to the Next question. In the next question, we have, so again, the answer is C, 4 volts. Let's move on to this question. In this question, we have a circuit that is also made of an inductor that is in parallel with a 2 ohm, with 1 ohm and 6 volt. Now consider that the switch S is closed at t equals 0. What is the current through the inductor L? But this time, long after the switch is closed. The word long after the switch is closed means that t equals to infinity or to 5 tau. Both are correct. Both are correct. 5 tau, we can consider it as an approximation to infinity. You can use the t equals to infinity in that exponential function that we have introduced for the current. Again, back to here, I need at t equals 0, the switch is closed. I need to calculate the current that goes through the inductor at at t equals after long time of the switch is closed. So let me redraw the circuit. If I am to redraw the circuit, I have here my inductor, my resistor, 2 ohm, 1 ohm, 6 volts. The 0 minus is the last moment before I took the action to close the switch. And the 0 plus is right the first moment right after the switching. So the 0 minus is the moment right before the switching. 0 plus is the moment right after the the switching. And this is the 0 plus is the moment that I asked for the voltage across the inductor right after the switch is closed, which means right at the 0 plus, right at the moment t equals to 0 plus. Now here we have the switch being closed at t equals 0. We need to calculate the current in the inductor long time after the switch is closed. Long time after the switch is closed, the inductor will be treated as a piece of wire. The inductor will be treated as a piece of wire. Why? Because if you recall, what did we say about VL? We said that VL equals to L di over dt. And long time means that the current now is not changing with time anymore. The current becomes DC again. So at that sense, the di over dt will be 0 and the VL will be 0. And a component that has a voltage drop across it equals to 0 basically means a piece of wire, an ideal wire. So because because the switch now is closed and for long time, the inductor can be replaced now with a piece of wire. So if an inductor is replaced with a piece of wire, this means this piece of wire that has 0 resistance will end up shortening out this 2 ohm. All the current now is going to go this path. No current is going here anymore because of this wire that is shortening out this 2 ohm resistor. So in this case, the current IL the IL now would be 6 divided by 1 equals to 6 ampere. Okay, is this clear? So no, I look at the value of the current before the switching, and I equate it to the value of the current in the inductor right after the switching. If you recall in the previous question, this when the switch was open, so that the moment t equals to 0 minus, the current in the inductor was 0. It was an open circuit. The source was in a broken circuit, so there are no sources of energy. So the current in the inductor at the 0 minus, at the t equals to 0 minus, was 0. And it will be the same at 0 plus. Right? The current in the inductor is not going to change between t equals to 0 minus, t equals to 0 plus. So I have I L at t equals to 0 minus equals to I L at t equals to 0 plus. Now, whatever the current at the t equals 0 minus will be the same at the t equals to 0 plus, only for that moment. And then it's either going to increase exponentially or decrease exponentially based on the value. Is the value that's going to is less, then it will decrease exponentially. Is the value that is going to greater, then it will go exponentially. So the behavior is always exponentially. If it's going up, it will go up exponentially. If it's going down, it will go down also exponentially. Okay? So always remember that the inductor in the at t equals to infinity, inductor is replaced with a wire in DC circuits. Why? Because in DC at infinity you already reached the steady state and there are no variation in the current, which means the voltage across the inductor will be 0, which means a component that has a voltage across equals to 0 is basically the definition of the wire, ideal wire. Okay, so let's move on to this question, and I think this is our last question for today or for this course. So in this question, we have the following circuits. We have two identical inductors. We have two identical inductors and two identical sources. As you can see, the inductor in circuit A is connected in parallel with 1 ohm. Inductor with circuit B is connected in parallel with a resistor 2 ohm. So at t equals 0, the switches were closed and they were left closed for a long time. And then they were opened again. Which resistor dissipates more total energy after the switches are open? Which resistor dissipates more total energy after the switches are open? Is it this resistor, 1A, the 1 ohm resistor in circuit A, or is it the 2 ohm resistor in circuit B? which one dissipates more total energy? 6 ampere. So which one dissipates more total energy? The 1 ohm in A or the 2 ohm, the 2 ohm in B? Uh, to explain this to you, let me open a new page here and redraw. So what's happening is I have this inductor, 2 ohm, 3 ohm, 6 volts, and then I have the switch closed t equals 0 for a long time. Then I also have here inductor, 1 ohm, 3 ohm, 6 volts. So switches are closed for a long time. If switches are closed for a long time, then the inductor will be treated now as a piece of wire, right? Long time. So at t equals to infinity for circuit A, circuit B, then I can now replace this inductor by a piece of wire. Why? Because now I'm talking about infinity times infinity at time infinity. So I can replace this inductor now with a piece of wire. So in this case, as I said, there is no current going into the 2 ohm and the 1 ohm, and all the current is going into the inductor because this is inductor now is a piece of wire that has shortened out this component that is connected with it in parallel. So here, if I call this one IA and this one IB, then IA would be as simple as 6 divided by 3, 2 ampere, and IB would be also 6 divided by 3, 2 ampere. So both of them will have the same current, right? Now the switches are open again. But now what happened is that inductor has stored energy in it given by the equation half L I squared. So notice that both circuits, they have in the inductor the same current, IB 2 ampere, IA 2 ampere. They are identical inductors. They have the same L, which means the energy that will be stored in this inductor is going to be the same for A and for B. So what do I have here? I have EA equals to EB, right? Now, when the switches are open, look what's going to happen. Remember, when the switches now are open, I have now a new T equals to 0. The switches are open. So the value of the current before the opening should equal the value of the current right after the opening, only at this moment. So if I am to redraw now the circuit, I can now replace this inductor with a current source, because before I opened the switch, there was 2 ampere in the inductor, and this 2 ampere has to stay the same in the t equals to 0. So now I can replace this inductor with a current source, and now the switch is open. I only have the 2 ohm now. Here I have the 1 ohm. So the current, so this is the moment of t equals 0 plus. This is for t equals 0 plus again. See this t infinity? Why am I having the time resetted again? Because I reopen the switch. Every time I do action, I consider the action as my t equals 0. So right here, when I close the switch, was at t equals 0. Then I said that right at t infinity, I had the inductor replaced by a wire, and this wire is shortening out this 2 ohm, and this is the current. Now for the next circuit, because now I reopen the switch, the reopening I did to the switch is basically that t equals 0. And now this value that was in the inductor will be in this circuit when I open the switch as my t equals to 0 minus. So right now here I have IL 0 minus equals to IL 0 plus equals to 2 ampere. The same thing here, IL 0 minus equals to IL 0 plus equals to 2 ampere. Now the inductor is going to act as a current source, and this current will decay exponentially. So the inductor, the stored energy, which is the same, look at the energy that got stored in the inductor when I first closed the switch and left it for a long time. The energy stored in the inductor was EA equals to EB. They were equal. Then when I open the switch again, this current start to discharge into those resistor. One of them in the 2 ohm, the other one is in the 1 ohm. But the total energy is the same. So the energy dissipated in both resistors, the total energy dissipated in those 2 resistors will be the same. The energy will be the same. But what's going to be different is the rate of the dissipation, the power. The power is going to be different. But the total energy that's going to be dissipated in both resistors is going to be the same. Which one is dissipating faster? Look at the tau. Tau is L over R. So the one that has the smaller resistor is the one that dissipating slower. So for the circuit on the left that has 1 ohm, it will dissipate slower than the circuit on the right that has 2 ohm, because the dissipated energy in the 2 ohm will be higher than the dissipated energy into the 1 ohm. This is the power that gets dissipated, right? For current sources, the higher the current, for current sources, the higher the resistance it sees, the higher the dissipation it also experience. Was this clear? Any question? Go ahead. Yes, if it's for the power, yes, the circuit with the circuit that has the inductor seeing higher resistance is dissipating in a faster rate than the circuit that has a lower resistance. Power. The dissipation, the rate of the power, the energy dissipation is the power. Power. What is the power? The energy is the integration of the power, right? And the power is the derivative of the energy with respect to time. So the power is the rate of charge or discharge of energy. B is dissipating faster. That's correct. If you think about it, look at the tau. Look at the tau. The tau for this circuit, tau for B, this is B, this is A. Tau for B is smaller than tau for A, right? Which means if you are to draw the, the discharge, the behavior of the current, you would see that the discharging here, if it's happening for the same current, one of them is like this, the current, the other one is like this, right? At the tau is different. So if you look at the power, this is the power that defines the dissipation power. It equals Ri squared. They dissipate the same energy, but at different rates. Tau is the time the current takes to elapse 67% of your starting value, right? If you recall, we said that it will be reaching down to 36. So this is if you're talking here about the 0.36, so this is tau for one, and this is tau for the other one, because if this is I naught, then this is the 0.36.7 or 37 approximately I naught. So you have two different taus. The time it takes for the current to be discharged down to 0.37% of its original value in the discharging. And the charging will be the 0.63, achieving 0.63% of the total. Any other questions before we stop? Okay, so we'll stop here.